Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is on multivariate time series, and in this lesson, we'll continue the estimation of VAR models with an approach for the order selection. In the previous lessons, we learned about the estimation approach of the unrestricted VAR model, along with advantages of using unrestricted over restricted VAR models. However, I also pointed out that one limitation is that the unrestricted VAR has many parameters. If the order is P, then we'll need P parameters for each time series. Thus, each regression will have P times n plus 1 parameters, which need to be estimated in each regression. For example, for a bivariate time series, the number of coefficients in each equation is 1 plus 2 times P, and the total number is 2 plus 4 times P. When we have n time series, the total number of coefficients in each equation is 1 plus n times P, and the total number is n plus n squared times P. This can be very large when n or P are large. If the selected P or the assumed lag order is unnecessarily large, the forecast precision of the corresponding VAR-P model will be reduced. Therefore, it's useful to have procedures or criteria for choosing the order P. Ideally, we would select the order P as small as possible. We do not want to use an arbitrary P which is too large. But how to select the order P? Order selection falls under the more general framework of model selection, when one has several models to consider and wants to select the one with the best performance, where performance is defined by some measure. Thus, the general approach for order selection is to fit the VAR model with P orders from 0 to a maximum order, and choose the value of P which minimizes some model selection criterion. The criterion is a sum of two components. The first is a measure of goodness of fit, and the second is a measure of model complexity. The criteria selects a model which balances goodness of fit and complexity. Classic examples of such criteria are the Archaic Information Criteria, or AIC, the Bayesian Information Criteria, or abbreviated BIC, and the Hannan-Quinn criteria, among other criteria. In all these criteria, the goodness of fit measure is the sum of square residuals. The only difference across this criteria is the specification of the complexity penalty. AIC is more generous in a sense that penalizes least for complexity, where BIC and an HQ penalize most for complexity. Thus, a BIC and HQ are indicated to be used to select order when we're interested in prediction in forecasting. Let's return to the simulation study where I simulated the VAR1 model for 3 time series, for a multivariate time series with 3 time series. In order to select the order, we can use the var select R functions in R, where the input is simply the multivariate time series. Here, I'm also plotting the AIC values for different orders of the VAR model. And this is the plot. And according to this plot, we can see that the selected order is equal to 1. And this was the order that we simulated in the VAR1 model, in the multivariate time series model. To summarize, in this lesson, I briefly introduced the approach that is commonly used to select the order in the VAR model. Thank you. Welcome. This is a time series analysis course. My name is Nicoleta Serban. I'm Associate Professor in the Stewart School of Industrial and System Engineering. This lecture is a multivariate time series, and in this lesson, I will illustrate the estimation and order selection of a VAR model. We'll return to the example in which we're interested in modeling the bivariate time series consisting of the unemployment rate and the interest rate in the U.S., motivated by the monetary policies in 2017 towards the increase of the interest rate. Because the time series are not stationary, since both of them have a trend, we'll analyze their first order difference, not the original time series. We'll first apply the simple AR model to each individual time series and select the order of AR for each of these two time series. Setting up 20 to be the maximum order, the selected AR order for the interest rate is 20, and for the unemployment rate is 12. But we're interested to capture the temporal relationship between the interest rate and unemployment rate. Hence, we apply the VAR model in R. The command is VAR. The input for this function is the data matrix consisting of the first order difference of the two time series in this example, the maximum lag for the model fit, and the specification whether to fit a trend, a constant accounting for the non-zero mean in the time series, no trend or no constant, or both. Note that the VAR command also selects the order, hence the specification of the maximum lag to be considered. These are variations of implementation of the VAR-R function with different types of deterministic trend along with the information criteria for model selection, here being AIC. For all types of deterministic components, the selected order is 12. We can also compare the selected order using other criteria. SC here stands for BIC. HQ and SC both select an order equal to 2. Note that these two methods, BIC and Hanan Queen, usually are penalizing more for complexity, and hence they select a much smaller order. P would be equal to 2. This is a very big difference from the order selected with AIC and BIC. In the next slide, I will show you the output when for the fitting the model, the VAR model, with order equal to 12. This is the output for the coefficients corresponding to the unemployment rate. In this output, all factors beginning with D int rate correspond to the lags 1 to 12 for the interest rate, and all lags beginning with D UN rate correspond to the lags 1 to 12 for the difference time series of the unemployment rate. From the output, we see that the largest P order for which we find a temporal relationship of the change in interest rate onto the change in unemployment rate is order 2, or up to 2 months. But for the serial correlation with unemployment, the coefficients are statistically significant up to order 12, or 1 year lag serial correlation. This could be due to the subseasonality in the unemployment rate. The coefficients for modeling the interest rate are on this slide. From this output, we find that the only statistically significant coefficients are up to order equal to 2. With an order equal to 2 would be sufficient to model the interest rate. Since very few coefficients are statistically significant for an order larger than 2, we'll test here whether the model of order 2 for each of the time series is plausibly as good of a fit as the one of order 12. That is, we test the null hypothesis that all coefficients for order 3 and higher are 0 versus the alternative hypothesis that at least one of the coefficients is not 0. For this, we employ the Wald test. In the R code provided on the slide, we first extract the coefficients corresponding to order 3 and higher. Second, we extract the covariance matrix of these coefficients from the covariance matrix of all the coefficients in a model provided by the VCOV R command with the input the model fit mode. Last, I'm applying the Wald test function in R, where I need to specify the coefficients and their covariance matrix. The option terms in this function can be used when we're interested in testing only a subset of coefficients. Here I'm using all coefficients since I already extracted order 3 to 12 coefficients from the entire vector of coefficients. The p-value for the implementation of the old test here is 0.044 for the difference in interest rate time series, and it's approximately 0 for the difference in unemployment rate. Thus, at the significance level of 0.05, we reject the null hypothesis for both time series, concluding that an order larger than 2 would fit the model better than a model of order 2. Next, let's perform a residual analysis to evaluate whether the residuals have constant variance, are normally distributed, and whether they are uncorrelated. The ARCH test is used to evaluate whether the residuals have constant variance. Since the p-value is approximately 0, we reject the null hypothesis of constant variance. We'll discuss modeling of non-constant variance in a different lecture. The normality test is used to evaluate whether residuals are normally distributed. Since the p-value is approximately 0, again, we reject the null hypothesis of normality. Last, the serial test is used to evaluate whether the residuals are uncorrelated. Since the p-value is large, we do not reject the null hypothesis of uncorrelated residuals. Last, we assess the property of stability. All eigenvalues in this case are smaller than 1, and thus the fitted VAR is stable. Next, let's look at the residual plots to explore further the non-constant variance and the non-normality of the residuals. These are the residual plots for the time series corresponding to the first order difference of the interest rate. The upper left plot is the residual plot, clearly showing non-constant variance. The upper right plot is the histogram of the residuals. From this plot, we see that the distribution of the residuals is somewhat symmetric but with heavy tails, hence the rejection of the normality in the previous slide. The rest of the plots are the autocorrelation plots of the residuals and of the squared residuals. These plots indicate that both the residuals and their squared residuals are uncorrelated. These are the residual plots for the time series corresponding to the first order difference of the unemployment rate. From the residual plot, we find that the variance of the residuals is constant. Moreover, the histogram of the residuals for the time series are closer to normality than from the previous time series, since the tails are more normal. Both the residuals and the square residuals seem to be uncorrelated, according to the autocorrelation function plots. In summary, in this lesson, I illustrated the estimation and order selection of the VAR model with a data example. Thank you.